Okay, so as already announced, the last part, at least from the workshops, is about micromagnetics.
So, with the field of micromagnetics, QASS has discovered a completely new area for itself a few years ago. And to stay with the analogy of the human system, if the analyzer is the brain and the acoustics emission sensor is the ear, then perhaps the newer micromagnetic sensor is something like the eye. But it's not only the eye, at the same time it's also a flashlight. Because our eye can only see something if we somehow cast light on it, which means the micromagnetic sensor is something active. Basically, it works by applying an alternating magnetic field, what would be then the flashlight, and then seeing what comes back. In the case of ferromagnetic materials, this Barkhausen effect occurs, which we have been talking about extensively. And this effect can provide information about many different properties of the component. And the whole thing happened non-destructively and also very quickly. This means we can do 100% testing and also 100% testing in line, because these measurements are a lot faster than classical measurements. And an example for these properties would then be classic hardness measurement. In other words, we can measure the surface hardness of components indirectly via Barkhausen noise. And for this application, we have created a new interface.
Right, and we see it here. I will explain briefly how it is structured. On the bottom left is a picture of the component to be measured. In this case, a belt buckle. In the upper left, you can, if you want, pre-configure the complete measuring sequence. This is especially useful for laboratory measurements. This means you can adjust how many components you want to measure, if you want to measure a component at one or more positions, how many measurement repetitions you want to perform at each position, how much positioning time is necessary. It gives you time during the automatic measurement sequence to change the component or to place the sensor at another position, and how long a single measurement should take. The middle column is dedicated to the measurement results. As soon as the result is ready, it is displayed both in tabular and graphical form. And the two plots on the right are, I would say, rather diagnostic. The traditional 3D process landscape is displayed on the bottom right. Each of these visible red hills is a Barkhausen signal and corresponds to remagnetization. And well, you cannot see anything in the upper right corner yet, but once the measurement is done, you would see the intensity of the Barkhausen noise in a single measurement process. And you can use it to evaluate measurement quality. With the two buttons on the right side, you can start either a single measurement or a pre-configured measuring sequence, as in this example. With the checkbox under magnet, you activate the alternating field. Yes, and now it starts. In the component picture at the bottom left, instructions are provided which part and which measuring position is next. At the same time, you see that all single measurement results are entered in the table and also in the graph. This is a quick measurement sequence. Now all results are ready. The measuring results table can be saved in the database. Exported in a CSV file or a PDF or something similar can be generated, which also includes the graphs. In the upper right corner, as already promised, you can see the intensity of the Barkhausen noise, the last of the 4 measuring processes that have been carried out here. Ideally, it should look like this, so like a rather horizontal line without major variations. It shows that the colleague who has carried out the measurement in this example has correctly positioned the sensor, has held still and not moved during measurement. If you were to notice irregularities by eye, you have to decide whether you really trust the measuring result or whether you would like to repeat measurement.
To specify classical hardness values as here, the measuring system must be calibrated, because hardness is determined indirectly through Barkhausen noise. This means we always need samples, components with known hardness, to measure them. Since the relationship between hardness and Barkhausen noise is usually rather linear, we can then calculate the hardness for all new components. Usually, the customer asks for the same scale as the one on which the hardness values of the specimen were given to us. These are usually determined by the classical hardness measurement. We need at least 2 values. The more values we have, the better it is. This way, we can then measure hardness more precisely. We have worked on this as well when redesigning the interface and can now perform it also using scripting. The aim was to simplify adjustments for the customer. The relationship is usually linear, but not always strictly linear. This means that it may be necessary to make certain adjustments in the calibration programming to find a perfect solution for a particular material. For this purpose, we have been able, since Micromagnetic workshop was the last one held, to use another scripting tool, the brand new Python operator. Python functions quite similar as JavaScript, but has the advantage that it brings along very powerful data analysis tools, which help us to evaluate data much deeper and also much faster.
Yes, and in addition to the belt buckle, we have brought another example with us. This will hopefully appear in a moment. Right, here in this example the specimen is a bearing ring, which can now be seen on the lower left corner. The goal is to measure 2 bearing rings one after the other at 8 different measuring positions. You can see here how the measurement parameters are adjusted. The measurement positions are located in 45-degree steps around the circumference. The magnetic field is activated and the measuring sequence is started. Once again, you see how all single positions are measured one after the other. This measurement task could be performed by hand, but it would be better to use a handling system or a robot to position the sensor. Yes, in the graph in the middle of the bottom you see the hardness curve, positions of the first bearing ring in red. And the second component is about to follow. Here you notice quite well that the second bearing ring differs in hardness. It has a little over 60 Rockwell. Yes, and what you also see is that even though both bearing rings have a different hardness, their hardness values are quite homogeneous at the measuring positions.
I've already said at the beginning that hardness is only one of the material aspects we can analyze and determine by using Barkhausen noise. Another parameter is material density. It is relatively easy to imagine if there's less material under the sensor, then we will also get a response signal which has a lower intensity. And precisely this property made it possible for QASS to plan and realize a fully automated measuring system for material density for the first time last year. The machine can be seen here in action. In the course of this development, QASS has added a new skill to its portfolio, that is robotics. A new robotics software was developed. This software is responsible for actuator movement and also runs on the QASS hardware. As in this case, these actors can be linear axis, but also robots could be used. What you can see here is that the measuring cell picks up the components from the sample parts holder fully automatically, carries them to the sensor, which is hidden in the box down here, and positions them. In this case, a laser distance sensor is used for precise positioning. You can see it on the left-hand side. Here, a measuring sequence for multiple measuring positions and several components is run fully automatically. At the end of the measuring process, the component is also fully automatically carried and put back on the sample holder. The operator can then remove and exchange the sample holder.
Yes, we have also created a new user interface for this application. I think it was the first one that we have developed specifically for an application. The interface also looks different from the examples presented before, as it has been developed in C++. Yes, in the upper left you can select the article to be measured. All articles can be stored in a database. And what is special about it is that we also store geometric information, such as the height or the outside diameter of the ring. Thereby, the measuring system can automatically check whether the correct article has been selected. For example, by rechecking the outside diameter with the laser distance sensor. Also here you can select the number of components to be measured, the number of measuring positions, and the number of measurement repetitions. When you press any of these buttons in the middle, such as Start Measurement, Pause Measurement, or Cancel Measurement, the analyzer software communicates with the robotics software and sends the appropriate commands so that its actuators move along the appropriate path. The measurement results are displayed both in the graph on the right and in the table on the bottom. Well, in this example the measuring process is almost finished. We wanted to measure 2 rings and only one more measurement value of the third repetition for the second ring is missing. Once all results are ready, they can be automatically exported into a CSV file. Another option that is now available is a Dfq Export. Yes, and as soon as all measurement results for a ring are ready, the software automatically decides whether the ring is okay or not okay. The user can define tolerance limits for the measured values. If the measured values are within the tolerance limits and the ring is okay, the entries in the table on the background of the graph turn green. In the opposite case, they would turn red. Well, in this case we have decided to match the graph with the component's geometry and to arrange the measured values in a circle. This has the following advantage. In case the ring's density is not homogeneous around the circumference and the ring is not okay, we can directly observe this on the graph, as the plot would then have dents and bulges and would not be completely circular. So that was our part to present. Thank you.